Welcome back. Welcome back. So, we're going to talk about the Rocky Mountain Trench, which is basically starts over here, continues over this way, goes over here, through here, through here, through here, through here, all the way to Flathead Reservation area. This region I've been talking about with relationship to Baja, BC, and the Missoula flood, etc. In one of my recent videos, I talked about this area and a paper on this area and its relationship to the process and how it really points to the Rocky Mountain Trench. And I found the name of the Rocky Mountain Trench. I didn't know what it's called. I just was like, this thing, this path, this over here that actually continues. So it's, according to modern science, the interpretation is that Rocky Mountain Trench is here, starting here, and then over here is called the Tintina Trench, which is really the same thing, just a different portion of it, in my interpretation. And so I've been saying that basically it's caused by current flows of literal ocean currents that were flowing here across Alaska. So the idea is that the flood is imprinted everywhere in the earth, where one of the aspects is that let's see, come over here, currents of the earth. An eddy was atop the Hudson Bay, an eddy was atop Michigan, and there's current flows over along western North America that are some coming southward. I just barely have it on this image here, and some going northward and interacting in this area. And those coming from the north side are deflected by the Hudson Bay eddy, as well as currents flowing in here. This runs into it, pushes it around, and goes this way, while also going generally down this path, this whole path, but especially along the boundary where it bends. It's bending and turning and going over here, and then goes down here with more velocity down this channel. So there's a highly erosive current flow that's traveling straight through everything in its path, cutting a path that's now imprinted. There's really nowhere else like this on Earth in this scale. Like, okay, so I decided, since I know the name now, I would just go to Google Scholar. I did this, and I just put in Rocky Mountain Trench geology, and I kind of looked around. So notice, before we even look at this, 1996, 1970, 54, 85, 75, 56, 89, 74, 26, 64. So this is the paper we're going to read. The Rocky Mountain Trench, a problem, which immediately caught my eye because of its title. I didn't know what it was about. I was just like, okay, that sounds like what I'd be interested in. And then one, and more recently, 2021, but 1955, 1966. Point being, by these ages, is the research in this area seems relatively minimal of late. So it's kind of believed to be established science, I guess. First of all, it's a trench and it's not the mountains, so people researching in this area are more likely to be researching the mountains than the trench within them. So it's just inherently less interesting from a, like, I mean, it's certainly not less interesting, but from a research perspective, like, people are going to want to research the mountains and things. They're not going to look at this really straight path so much and be like, that's what I want to study. And same for publications, that's what I want to publish, or that's what I want to sponsor with funding of, like, a grant to research it. So it just doesn't have as much attention, it seems, especially of late. So if we go to Rocky Mountain Trench and just check out the Wikipedia, also known as the Valley of a Thousand Peaks, or simply the Trench, it's a large valley on the western side of the northern part of North America's Rocky Mountains. Let's go to geology. Right lateral strike slip movement of the Tintina Fault on the Tintina Northern Rocky Mountain Trench may have begun. So it's basically, let's go up a little further. The Rocky Mountain Trench is closely aligned with the Tintina Trench, which was this portion up here in this area. It's just got like a gap that makes it unclear that they're connected, but this gap is directly across from the Hudson Bay. Essentially what's happening here is that a huge eddy is here, so its width is generally greatest where this is, so it has like an actual interaction over here at the greatest width that then leads to no mountains here. Mind you, this is all in an earth expanding framework where the earth expanded is not still expanding because it was the global flood that occurred, according to geology radiometric dating, from 541 million years to the Holocene, the end of which was around the Younger Dryas and the Missoula flood and so on. That's why they're related, even though this is dated much earlier, like millions of years. So like people in modern geology studying how did the Missoula flood happen aren't going to look at the Rocky Mountain Trench through the same lens where it may have a relationship to the flooding in Washington area, but it does. So we're gonna look at this paper. I got a bunch of basically underlined things as I read it, but let's look at the abstract. Rocky Mountain Trench, A Problem by C.H. Crickmay, received August 1964. So this is 60 years ago, thereabouts, when this was published, and received at least. The Rocky Mountain Trench is defined as the 1,000-mile valley which marks the west side of the Canadian Rocky Mountains. This whole video is going to be me reading the details, so if that's not appealing to you, so be it, but this is really interesting. I highly recommend sticking around to learn about this trench and why it's not really compatible with the modern interpretations, where it's effectively a fault. So if I got fault, like fault. The result is that terrains to the west of the fault system have moved toward the north. So it's basically there's a fault there that's creating this pathway because there's motions opposite one another, or like the continents there, and then motions to the west that are creating this fault. But the evidence clearly shows that's not the case. We'll see why in a minute. Okay, so several minutes as we go through this video, this paper. The background of the trench as a problem is examined, and descriptions, geographical and geological are given. Previous work on trench origin is reviewed, and note is taken of the seeming inapplicability of accepted erosion theories to the making of the erosion-made trench. And a hypothesis is offered. So mind you, when he's talking about erosion, they're talking about like slow and steady processes and not really envisioning a highly pressurized current that is flowing across the entirety of the region that especially concentrates along resistance that then flows down a channel that it etches. A hypothesis is offered in which the combined action of drainage hemmed in by bordering uplifts, guided headward erosion, which is at the front of the stream, which is basically what I'm saying effectively, is a current is flowing through, cutting, and it's probably at a higher depth, but it's also at a lower depth, and as it travels at that lower depth, it's cutting, in a headward erosion mechanism. Lateral corrasion, which, let's see what that is. I guess it's just sideways. We'll get into that when we reach it more in depth. And streams repeatedly reversed by continuing diastrophism, which is motion of terrains, basically. Process of deformation of the Earth's crust, which involves folding and faulting. So deformation of the Earth's crust, which this highly pressurized current is doing to the Earth's crust in this region as it passes through. Okay. Is suggested as the excavator of the trench, all of those mechanisms. A valley characterized by the puzzling peculiarity of continuous depth without a consistent gradient. Okay, so the distinctive characteristics of the trench may be summed up. The trench is A, very straight when compared with the typically crooked, bending, and irregular outlines of most ordinary valleys. B, broad bottom throughout, in great part flat floored. So it's like if we go here, like it's broad bodied throughout. Like this is the modern river. This is the trench. Broad bodied. Oh yeah. In great part flat floored, without any unified or consistent tendency in gradient, without consistent correlation between its dimensions and the local volume of drainage, open to the escape of existing drainage at more than one place, actually 6 places, with several old abandoned river outlets higher than its present day floor. So like, what's that water? Where was that water like traveling? Are we sure it wasn't at a great depth that like spanned the entire width, like a river passing through here, that then was deeper as well and allowed for outlets? That like now there's an outlet here, but like sometimes, for instance, where is the one that I'm thinking of? If we follow this back here, this one, which I talked about a couple videos ago, comes over this way, and then it kind of just like, where did it come from? Like there's a path here, but if we keep going up this way, like right here, there's not really a river through it, like cutting across. It's higher, so if it had a really wide at the width of the trench, as well as deep because of how much water was there, that it actually could get over terrains like this, then it could have flowed even though it didn't continue to flow. Okay. After like the water receded, basically after the earth expanded, all this water that was on top of the continents while the flood was happening was able to retreat into lower elevation of the ocean. Before the ocean floor existed, the water, well, there was a time when the earth was stable. All the continents were conjoined. There was water on the surface, but it didn't cover the surface of the earth. And then there was a time, intermediary time, when water started to flood the earth. And it moved. It didn't just like sit there. It was moving in high velocities and like etching the continent boundaries where there was interactions of currents that were causing upward and downward motions and currents along boundaries that then etch the boundary and shape the continents and shape the whole earth effectively. And then once it cut the continents apart, the newly forming ocean floor below, because there was undercurrents of basically basalt magma that were flowing, that then were able to fill in the space between the continents and create ocean floor. And then the water had somewhere to retreat to, so it did. But it didn't do that until basically the Holocene is when it fully was able to stabilize into the oceans. Okay. So that's the paradigm in which we're looking at this paper. And consider the evidence. That's all I can say. Consider the evidence in view of what I'm saying and see if faulting makes more sense or if a really rigorous current flow through the region actually makes sense with the evidence. Drained by two or more unrelated streams with much evidence of stream shaping in its walls, with minor evidence of glacial erosion and deposition, which basically is saying glaciers are not like the cause of the trench. With its axis of length having a more or less consistent relation with the regional strike of bedrock formations, with bedrock structure varying along its length, thus being different in the various parts of the trench. Okay. In all parts of the world, there are valleys that, though smaller, have nonetheless the same kinds of earmarks. So all those things we just said, they're everywhere. So connecting that to the flood, in all parts of the world, there are valleys of the same nature, just smaller. This one is very extreme. Furthermore, they are all scientific mysteries. Mind you, this is 1964, so some of the statements like this may have not been the same if they were to be living today and have the same perspective. I don't know the depth of research that has gone on this topic and how people feel about things, but I can say with certainty that they present some evidence that it is what it is. It doesn't matter when they looked at it. Okay. They all pose the same problems about how they came to have the distinctive peculiarities of their class. And then they list some, which maybe I should look into. The very word problem has attained a sort of lack of status. But in an inquiry of this sort, it has to be used, and perhaps frequently. May it cause no underestimation of one of the really great enigmas in the science. For the existence of the Rocky Mountain Trench is an enigma. There is no interpretation of the trench that satisfies all competent experts. The origin of such valleys is less a question that has foiled the best mental powers that have so far investigated it. The age of it is a question to which too many divergent answers have been offered. It has been supposed to have existed as a master valley from early Eocene time, Can any existing valley be as old as the Eocene? Maybe if there was a highly pressurized current passing through that kind of made it a certain way, but then occupied its space so it couldn't just break down as easily, so that radiometric time passed, and then it started to stabilize in a more modern time where it didn't degrade as much, perhaps. The age of the trench must be held a prime question for investigation. So some features, low flat-topped outcrops are quite numerous. Others exhibit forms of small-scale lineation roughly parallel to the length of the trench. So there's other within the trench there are parallel with the trench length lines, lineations along it at times, which a current flow passing through could do for sure. The bottom of the trench is a surface constituted largely of carved rock. The valley walls of the trench are a very variable character. In Montana, they are gentle and of a regular trend. Gentle, almost as if the current is no longer quite as rigorous as it reaches Montana. In southernmost British Columbia, they become much more abrupt and regular, in fact more wall-like, which is earlier in the current path. The side slopes vary from straight to terrace to broken and irregular. In some places they show a downwardly diminishing gradient, but nowhere do they exhibit a close parallel to the form of the sides of the letter U, which I believe they're saying, sorry, maybe I'll make me a little smaller and down. Okay, which is related to glaciers, probably is why they said that. In the vicinity of Cranbrook, let's see where that is real quick. Cranbrook. So very nearing the Flathead Reservation area. In this area, the east wall is much steeper than the west and more sharply definite in its lines. So just looking at this, east wall is more, they said steeply sloping, steeper, and sharper. So if you imagine a current coming down here, but up here it's going west to east, but then it runs into resistance over here in this region and is caused to go this way. Through the trench, basically, at least the part we're analyzing, it certainly goes through it all, but through the trench, coming down here, looks like it might have actually ran across this way in part. That might be part of why. Cut across this way in part. Went over top and created like more of a gentle slope. But this is not a continuing tendency, for in some places the west wall is notably the more abrupt, and the walls are more or less similar to each other, both being steep and rugged. The highest and roughest of the valley walls are those between Golden, let's see where Golden is. And I don't know if I can, there we go, that's probably good enough. So this area is the highest, steepest, roughest of the walls, where it looks like there's compression on this side and on this side, leading to it just cutting through a more like a channel like this that then has a wall and a wall. Okay. Despite their commonly rugged character, many parts of the trench walls are terraced. Some of the terraces are broad, level, remarkably flat, and well preserved. The positions and extents of the terraces are extremely variable. Most of the terraces bear thin river drift covers. Many tributary valleys join the trench and break the continuity of its walls with gaps great and small. All the large rivers that drain out of the trench leave it through breaches of great size. The greatest gap in the continuity is in the Musicom area, where the southwest wall has been erosively gnawed away for 100 miles. The great size of this discontinuity seems to be related not so much to the volume of the Fraser River, which leaves the trench by way of it, but to a long, complex, and little determined drainage history. Most of the tributary valleys, or maybe like a region, let's see where this is. I don't want to like continuously go back and forth to see where places he's referencing are. Is it over here? Okay, yeah. We're this side. So this area, notice this path here. Not just this path here, but also over here. That's how much water is involved, where there's a straight path on the opposite side of the Rockies, the east side, that's physically interacting with this current and causing a break-off current to go this way, eroding over here 100-mile width, across flowing this way. Most of the tributary valleys are comparatively small, break the trench walls for no more than a mile or two, are broadly V-shaped or neatly terraced gorges being most common. Some are broad and flat floored, some are of U-shaped cross-section, commonly associated with glacial erosion. Okay, so I'm going to speed through this. I guess that was the end of that one. There's a lot. Let me just scroll down. I read the whole paper. A special type of gap in the confining walls must be noted. This type is now let me just read this whole thing, I guess, is the river-made mountain pass, which, though low in comparison with peak elevations, is now too high to carry drainage from the trench. Moy Pass stands several hundred feet too high to affect the main drainage. Most of the passes are in the Rocky Mountains. That is, they pierce the northeast wall of the trench. Going like this way, like out of the trench, but at an elevation. I'm not sure. Let's see if we can find that one too. Probably that's good enough. Moy Pass. Maybe that's not it. Maybe over here. Over here. I don't know. Over here, maybe. Not sure where that is. But the point being, they're several hundred feet too high. Here, and then here are some of the other ones. All of them formerly carried water from the trench. He says from, not to. So these several hundred meters too high, or feet, carried water exiting the trench, like branches from a tree or veins from an artery kind of thing. There is no correlation between the dimensions of the trench and the size of the rivers flowing in it in general. Like that's just an observation that is made. But there is some correlation between the volumes of rivers where they leave the trench and the stream levels at the places of departure. In other words, the larger the river, the deeper it has cut down in the latest stage of its history. So basically, as the water retreated from the earth, it started to drain. So at one time there is a depth of water that's flowing, and there's resistance along the ground because the ground is there. So water above, kind of like air, is more able to flow freely above. So it's not as necessary for the water to travel along the surface, but as the water reduces in the sheer quantity that's flowing through, but is still flowing through, it then has to cut into the ground. It's more able to. So it would make sense that as things stabilized, current flows that were the strongest ways, the larger paths, the larger rivers, were able to cut deeper at the latest stage of its history. There's also another correlation between rivers and geography. The 4 southern drainage systems lie in the region of the high mountain elevations, and they all drain to the Pacific. I'm not sure where he's referring to, but generally, as we're approaching here, this current's coming this way. So it's running into resistance, so it is more, and there's resistance over here, so it's caused it generally go over to the Pacific. Probably these currents, I don't know exactly. Generally, the Columbia River here to the Pacific, which comes up this way over there somewhere. The 2 northern systems lie in a region of low mountain elevations and both drain to the Arctic. I'm not sure where that's referring to. Maybe over here, like right here. Goes this way. Over here. Which possibly was currents coming this way, down this way, across here, through, and in this pressure being pushed in, but then this is flowing this way, so it then bends around this way and joins. But then once the currents stopped flowing, then it was able to flow the other way because it actually went to the ocean. It was going uphill in essence. Now it's going downhill because there's not pressure behind it pushing it uphill. In that time, it was traveling uphill. Existence within it of subparallel tributaries, about latitude 54 degrees. The trench is not a single clearly marked valley. For about 100 miles of its length, it is greatly increased in width, and its bottom is divided by several lengthwise intra-valley ridges, so 54 degrees, I believe is around here, or no, 54, oh yeah, here, he's probably talking about this, where it has one here, one here, one here, here even, possibly here, maybe I can zoom out real quick, which is here. Get rid of that. It's here in the grand scheme of things. We're just past this. Thus, arises an area of multiple drainage and complex surface forms. So, mind you, What is a fault? If this is caused by a fault, something sliding past North America in part, literally, then what is it doing this for? Why is it creating drainages like we were just talking about at a higher elevation where the trench drained out there? It could be argued, I guess, that there was a time that the trench was just not as deep, perhaps. Only on the northeast is there a rail boundary wall. Okay. The outstanding peculiarity of this part of the trench consists in the great lengths of relatively straight stream courses draining in adjacent subordinate valleys within the trench, nearly parallel to one another, though in many cases in opposite directions. I didn't know what to make of that. It's probably because it's running into resistance. It's like going back, but then it's running into resistance and going back kind of thing. And some circulation path that's caused the break off. The principal drainage deviates from the main trench for 20 miles north of Donald. The supposition here being that the Columbia River is out of the trench for 20 miles and then goes back into it. Between Bluewater Creek and Bush River, the Columbia is pushed against the southwest wall of the trench by a large rocky intra-valley upland. Against the wall. Okay. Geological description. The trench is underlain and bordered by various rock formations, mainly Precambrian and Paleozoic. In Montana, it lies within a terrain of Proterozoic quartzites. In southern Canada, sedimentary formations from Proterozoic through Cambrian and Devonian to Carboniferous flank the trench on both sides and appear in numerous low outcrops in its flattish floor. So I would say this kind of points to the time in which this was happening. If it's related, it might have just these might have existed, and then because essentially I do believe as the Earth expanded, before the Earth expanded, Alaska was more up here, at least the portions that were there, physically up here, and then kind of like this, and then it and Russia did something like this to then arrive at their present state. Russia might have been even more it might have been more like this though, when slid past it, kind of thing, to then energetically couple to Russia, and then the current was able to go across. So I kind of interpret that that's what happened, is that the current was not flowing like that until the Earth expansion started to happen more, to the point where Alaska moved to its present relative position to Asia, at least in terms of pointing at Russia, so that currents flowing out of Asia that were going generally across here, across this way, ended up going in here, although maybe they were flowing this way. It's possible they flowed along the Mariana Trench even, and were caused to flow along this way, and they got a width flow over here, go atop this region, and then flow across, where then they ran into resistance of current going this way, and just the pressures that then caused them to bend over this way. But other pressures from Baja BC accretion, so there's a current flow generally going this way, up here, pushing all these materials literally into North America to accrete them onto Western Canada and Alaska, and some in Washington as well. That was then pushing here. So this current was there's a current generally coming up this way that's pushing right here. And this current deflects around it and goes down this way. Once it passes that upward current, so it goes this way. So that probably was happening more so in like the 150 million to Holocene time frame when this current was especially flowing, possibly even more so after the Cretaceous, after 65 million radiometric dating, like more recently. Okay, and then flank the trench on both sides. There are many not inconsiderable bodies there of igneous intrusives of Precambrian age. The structures are complex and consist of, which is before the Earth expansion process, are complex and consist of compressed folds and tilted blocks broken by faults, like they were under pressure. However, except for the trends of folds, many of which roughly parallel the trench, there are no dominating formations or structures uniquely correlative with the trench. So geologically, they're saying there's really not that much to look at to see that trends the same as the trench, except for these folds. From the Columbia River portion through the Fraser River area, there are early Paleozoic and Proterozoic formations in the trench. Much of this rock is highly metamorphic. Even in the far north, Cambrian, Devonian, and other formations appear widely in the bottom of the trench. It is a surprise to discover that much of this bedrock, at least below the highest slopes, is considerably decayed and quite different in that respect from the fresh rock of glaciated country. So again, another, like, it doesn't look just straight carved by glaciers, is the point. The only formation peculiar to the far northern region of the trench is a clastic deposit of Paleocene age. This young formation, the Sifton sandstone, is of more interest and significance than any of the older rocks. The Sifton beds lie on older Precambrian and dip steeply northeast. They terminate with very steep dips against a fault that parallels the base of the northeast wall. Thus the formation enters fully into the highly disturbed structure of its area. So it sounds like it's running into a resistance. The current is moving this material and the material itself and physically folding down into the earth by currents. Like, it's not like there's not any evidence of this fault system. It's just that this is what currents can do, is they can cut the earth deep down to the point where they cut the entire continental crust. And it looks like there was a current involved that was bringing this Sifton beds to actually dip in at a very steep angle against resistance, if I'm reading that right. The circumstances are highly significant with respect to the history and manner of origin of the trench. Another young sedimentary deposit occurs in the southern part, a Pliocene deposit, and later on it says maybe Miocene. And this paper generally doubts the longer, older dates for some things like this. They're like Pliocene, but then Miocene really stretches. Like, this kind of stretches, but Miocene really stretches the imagination, I guess. It's more about that, like the capacity to envision how it could go back that far, but the flood certainly was happening, so like there's probably some credence to this and where they're coming from in terms of the evidence. Deposit lies horizontally on a basement of Precambrian. Most of this material is very fresh sediment and scarcely consolidated, but the pebbles and cobbles in it are much decayed, as though from pre-deposition weathering, like the flood weathering it, a sharp contrast to the Pleistocene and recent gravels, like when the flood is slowing down, and perhaps actually even the glaciers are forming, like there's actually freezing of the water that's helping to prevent this weathering, so that the particles, pebbles, rocks are moving contained and not exposed to tumbling, kind of thing, that then weather them. Its fossil content consists of warm climate species. I thought that was interesting. Made me think of a flow like coming from over here up this way, going across here and up this way, and possibly even across this way, up this way, and then over that way. I haven't really reasoned through that part that much. The sediments appear to have been laid down on an old trench floor, which now stands that height above today's erosive activity. So notice there's depositions increasing the height too. So really, like, again, going back to that concept that, like, this was deep and still overflowing at hundreds of feet above the floor. So, like, if there were later deposits of sediments, the occurrence demonstrates the Pliocene depth of the trench, a significantly great depth of the order of 5,000 feet. The trench, 5,000 feet of water flowing through this channel, pretty much. Many of the flat, near-level bedrock surfaces in the trench are covered with young gravels, sands, and clays. Silty clays and boulder clays are generally assumed to be Pleistocene. It is noteworthy that few, if any, Pleistocene deposits in the trench exhibit a really typical glacial surface, though rough, subparallel lineations exist in places, which currents can do, where they, like fingers, like, it's one arm, but it's a hand with multiple currents. Fluvial deposits of Pleistocene and recent gravels and sands constitute most of the thin floor carpet which covers so much of the trench bottom. The truth appears to be that the subjacent, so below, the subjacent rock bottom is also remarkably flat and near level over sizable areas. There are no considerable bodies of post-Proterozoic igneous rocks in the trench, but there are a number of very small ones. So anything during the Earth's expansion process, there don't seem to be any considerable bodies of igneous rocks, but small, very small ones. I don't know what to make of that exactly. It is not yet possible to make out the full importance of any of these younger igneous rocks. Their scarcity has, perhaps, a connection with the origin of the trench. I was thinking maybe just the fact that there's this current cutting through, and maybe even that there's current, like, heat exchanging with below the earth in a way that prevents igneous activity. I don't know. Much has been written and published in the hope of proving that the area of the trench is one of peculiar and significant structural character. A careful reading of the relevant geological literature seems to reveal a widely felt wish to establish that a zone of higher than ordinary concentration of faults marks the trench, and to hypothesize the existence of some faults that cannot be substantiated. So now we're getting into some of the really good stuff. The great faults postulated and mapped by Daly, though never really found by him or anyone else, set a fashion not yet discarded. Meaning, it pretty much set a precedent, and since then we've just like taken these faults and not rigorously considered alternatives. Many have referred glibly to the structure of the trench, as though it had already exhibited a peculiar structure recognizably distinct from adjacent areas. For example, Headley and Holland wrote, "The underlying structure, however, could continue," which was closely matched by Armstrong, who said the underlying structure could possibly continue, and North and Henderson state that the trench was an active structural feature. Statements of this sort show that some geologists felt that the trench must, and therefore does, have a separate and peculiar bedrock structure, even though this structure has not yet been found. Again, 1964, but even in this paper, they're like, maybe in the future we'll find some things. In addition to its being deniable throughout, a feature of this doctrine, which a reader finds unenlightening, is its questionable conclusion that the two sides of the trench are fundamentally different. In all studies by the writer, both of the literature and in the field, the actual differences have seemed no more than those commonly met with in the opposing sides of all broad valleys in regions of disturbed structure. Again, some writers have attempted to distinguish in the trench a relic of a paleogeographic feature. They have tried to identify its location with Paleozoic shorelines. This is rather a far-fetched likeness. The fact is, Paleozoic formations cross the trench without showing evidence of close approach to their ancient shores. Further, the suggestion has been urged that the trench brings into juxtaposition over at any rate a great proportion of its length two completely different geological provinces. For the mountain, I'll just read the rest of this too. The word geological seems to be used here in the expectation that it will include the meaning of paleogeographical, but if it did, the statement would lose any emphasis and some of the truth it may hold. For the mountains on opposite sides of the trench are different geologically because they are now of different structural status, which I think he means like named differently, and as a result preserve mainly different parts of the geological column. Finally, which also maybe is to do with their elevation and other like imbalances between the sides. Finally, it is scarcely the trench that brings them together any more than 42nd Street brings together whatever there is on two sides of it. Okay. We are steamrolling. We got, in view of all the insistence on dislocation, it will be well to make clear that no one has yet demonstrated any more faulting in the trench than he is forced to recognize in the mountains on both sides of it, if as much. So there's faulting on other sides of the trench too. If we're recognizing this faulting, like it's just that the trench, to explain the trench is this major fault system, but then to ignore the evidence elsewhere, like it definitely, this is just so many good arguments against the modern interpretation in this paper. That's hilarious. 1964, he's just crushing it. Admittedly, the structures of the area are incompletely known. So this is where he says it. Admittedly, incompletely known. And it may be well, therefore, to summarize what is known. Attitudes, I don't know what this meant. I don't think it's altitudes, but I don't know what that means in terms of what we're talking about. Attitudes among the sedimentary and metamorphic formations within the trench have been recorded at all angles from horizontal to overturned. Whatever that attitudes means in that regard. In most places where markedly dipping, the bedding and any foliation in the rocks strike roughly parallel to the length of the valley. The best instance of a fault paralleling a trench wall is one that follows the base of the northeast side at latitudes 57 and 58 degrees. So not even that much of it. Many faults run into the trench from one side or the other. Some cross it at oblique angles. Evidently, the principal known structures are highly similar in kind to those of the adjacent mountains. It is possible to test the opinion that the area of the trench is of distinctive and peculiar character, and that it brings together completely separate geological provinces. One may remove from a geological map, I didn't quite understand what they were saying, but of the region, all such identifying marks as drainage, contour lines, and large bodies of recent alluvium, and then look at for the trench. Nothing in the remaining bedrock will reveal the location, outlines, or extent of anything in the nature of a trench. I didn't really understand what they meant by that, but up and down its whole length, it is plain that the trench has been imposed on a region inviting to trench making, no part of which, however, has caused the trench to be made. Broadly, the Central Rockies on one hand and the Purcells and related systems on the other hand, structurally high with respect to the wide area between, and in a narrow though varying zone in that wide structurally low area lies the trench. And that is perhaps the most significant tectonic observation that all our accumulated knowledge permits. And then I finally realized that I didn't actually put the abstract in. Possible origins of the trench. A number of hypotheses have been advanced with a view towards explaining the trench. Their achievements converge, however unintentionally, into a conclusion that explaining such a phenomenon achieves nothing. Why are we even bothering? Who cares? It doesn't even matter. I'm writing this paper about it. Ultimately, from studying it, I came to the conclusion it doesn't even matter. It's just a trench. In the many papers that have come out, much has been said, and rather cloudily, about structural control and the possibility of a graben in the making of the trench, which suggests, so if anyone doesn't know, graben is like this, go down like this, Horst graben, okay. And the possibility of a graben in the making of the trench would suggest that some have thought a diastrophic construction as a possibility, which was the earth deformation by faulting and folding, and just processes rather than specific processes that kind of tend towards modern interpretations in plate tectonics. However, neither diastrophism nor constructive process as a shaper of the surface has been forthrightly mentioned by any contributor. There may be a good reason for this, for nowadays, even among those who toy with such expressions as fault control, it is perhaps realized that the only structure which brings itself into relief on a great vertical scale is the broad upwarp. Ordinary small or local structures cannot in any way give themselves surface expression. The only exception is the fault, and no fault scarp has any great vertical dimension. Fault-line scarps of notable dimensions occur in the trench, but it is well to be clear that these are denudational. I don't know how to say denudational. So eroded. That these are eroded features that happen to show up now because erosion in the trench happens to have exposed them. It is therefore both confusing and obstructive to clear communication of thought to hear of fault control and structural control in a discussion which never gets as far as to straightforwardly deal with actual constructive and destructive processes. Only one of the many hypotheses that have appeared is sensitive to the question of how a valley of such continuous depth and of a length and gradient such that no one river can drain it may become excavated. Most of the discussions in print consist of highly sterile rationalizations about structural geology, with the actual trench left out. Even North and Henderson remark in the last paragraph of their considerable paper, nor have we so far accounted for the linear structural zone being represented by a physiographic trench. To a reader, it sounds as though they had recollected all too late that the trench is a valley, and calls to be studied as such. A notable defect in this, as in most discussions of the origin of the trench, is a total lack of reference to the work of destructional process. Denudational history is given no place. So no one's really considering erosion. And even where the thought of structure dominates the writing, the agent of the making of all structure, diastrophism, has not been brought into the argument. They have failed to perceive the trench problem. Failure to balance constructional, which the current compacts material and brings things together, but also cuts through it and destroys the formations, constructional and destructional processes, and their results against one another, is a serious shortcoming. Daly named the trench, but his remarks seem to show that for him it was very much a vacuity between two more positive, more interesting entities, the mountains, that's just how it is. This trench is certainly not considered as interesting as other things, but it really is interesting. Last 19th century doctrine flatly rejected the thought that all topographic form is much younger than the broad uplift of which it forms a surface. And you can read that, I didn't. Blackwelder represents the more up-to-date stand that many, if not most, mountain ranges are not constructional, but destructional forms. This is the 20th century thinking. Those which cover the trench prove that to be an excavated hollow, eroded. A great part of the trench walls and bottom offer testimony, like shallograms, that they owe their making to the work of streams, like shallograms. They still bear deposits of sand and gravel on carved terraces at all levels except the highly wasted uppermost slopes. These trench surfaces therefore have to be interpreted in terms of epigene processes. So epigene, taking place or produced on the surface of the earth, not fault processes in the earth. This is surface currents have to be interpreted. These trench surfaces have to be interpreted as surface processes, and the space they encompass, namely the trench, would seem from that evidence alone necessarily to be a void formed by destruction, i.e. eroded. As things stand, one hypothesis has followed this up and attempted to interpret the trench in terms of its possible surface history. Schofield's paper has been unwarrantably neglected. What a surprise. What a surprise. Schofield's contribution, although they point out some reasons like typo. Oh, missing word. But they wrote west, they meant east, or whatever it says. East meant west. Schofield's contribution consisted first in seeing the problem, the puzzle that lies in erosions seeming to have wrought continuous depth without a consistent gradient. He recognized the general prevalence of drainage from the interior of British Columbia eastward to the region that is now the plains, an arrangement entirely dissimilar to today's conditions, kind of like I was saying with the current to the Arctic, the perception of which was less a radical departure and an inspired one. And then yada yada. In that way, the essentials of today's drainage may have been initiated. I don't know what that was referring to now at this point. Maybe I should have underlined some more, but radical though it may sound, this was by no means a preposterous hypothesis. No subsequent attempt has approached its breadth or strength or its clear perception that the origin of a valley, even that of a valley lying in the midst of bristling, disturbed, and ruptured surfaces, lies in the sphere of surface process. The direction of flow of the primitive Fraser River from Tête Jaune to Giscombe reversed twice, or maybe even more times, I believe he says at some point. If the investigator were to include in the general trench problem the origin of all valleys that are, in their resemblances, trenches, that is, open at both ends, low throughout, and drained by two or more unrelated streams, Schofield's special answer would not be fully adequate, but no other answer yet given gets as far as did his in discerning the real problem. At this point, the question is there a general answer? The theories of erosion. On the face of it, there appears to be no geological process that is known to make a trench. It might be well, therefore, to review the theories of erosional agents and their work. To begin with, weathering and wasting achieve results only when favored by elevation and the existence of a strong slope, unless current flows, remember, unless current flows are really potent, like cut through. Is that a mountain? I didn't even notice. Who cares? I got so much pressure behind me, I'm going. The mountain can come with me if it wants. I don't care. I'm going. I ain't bending in my path either. Going straight ahead. I got nowhere else I can go. That mountain's insignificant next to the pressure behind me and to the sides. I'm going through it. Four natural agents corrode the surface of the earth. I guess corrode. I don't know. Some variable or variant of corrode that's geological. Wind, running water, standing water, and flowing ice. Wind moves broadly. It becomes channeled and convergent only when favored by ready-made channels. Again, unless the currents are really strong and directed, I guess, then perhaps it can erode into the earth in ways that are not appreciated in what he's saying. It moves only the fine-grained rock debris. Nothing suggests that wind is a perceptible contributor to trench making. Certainly not this trench. Running water tends, or any trench really, wind is probably not related to trench making, but it probably does more than is appreciated, is my point. Running water tends to channel itself. Check, that's in the direction we're talking about. Even on flat ground and with barely perceptible slope, I mean, especially, it doesn't even matter if there's slope, if there's pressure behind it and around it, if it's contained enough, at a depth enough, then the slope doesn't really matter. It's still going to flow on the slope, especially if there's pressure behind it, pushing it up the slope. And it tends to hold together in a stream of limited width in the lowest path accessible to it. It carries all manner of rock debris, the sizes carried depending on the force exerted by the moving water as a consequence of its velocity, and entirely This ain't limited to like water flows we see today. Oh, waters only can flow this velocity in modern times. Water can flow any velocity with enough pressure and containment. It's gonna flow as much as those values instill into it. It doesn't really matter. Entirely independently of its energy. A secondary effect is that the moving debris abrades or corrodes the ground over which it is moved, so that it helps in the process that we're seeing. Stream corrosion of all sorts is markedly, I wonder, is that like an actual, I gotta see. I don't know why, what's the difference? It must just be a geological term. Refers strictly to the strictly mechanical wear of bedrock by moving detrital and other materials during their migration downslope under the influence of gravity. B, they're further, so just in equilibrium conditions, yeah, downslope is the way water travels. But if, like, for instance, ocean currents at the bottom of the ocean, they don't just stick to the bottom of the ocean. They come up, they go up, they ramp up, they go up things because there's pressure behind them and around them. So they can go up like an island side, like up well in ways, go up the continental shelf boundary. They're not restricted. It's just they're not as intense or as focused as this current was. But they can do those things in the right conditions. It doesn't have to be down, just under, basically uniformitarianism interpretation of just same process as we see it today, apply them to any other time, the end. That's all we do. No, that's not the full extent of what's possible and what happened. We have to actually account for what happened, which is not the same. The flood happened. The earth expanded in the process. There was a ridiculous amount of things that happened that are not happening today, catastrophically. A secondary effect is that the moving debris, stream corrosion of all sorts is markedly selective of the less resistant kinds of rock formations. Less resistant kinds. So, like, if the current is moving under pressure in a direction and it's able to cut through in front of it because it just overwhelms everything, where like the side pressures are from the water on the other sides are holding it down that channel, then it less resistant could just mean whatever's in front of it. It doesn't have to be like exactly following the path. That kind of implies a more general setting where water is just like there's a mountain, water goes down the side, and it flows according to the path that, like, yes, and of course that's what happens, but also like that's not entirely capturing the full spectrum of what has happened, where sometimes it just cuts through things because there's not enough resistance in front of it, so it cuts through it, like making this trench. The direction in which it makes progress is in some part the result of its being more rapidly successful against weaker resistance, like a highly pressurized current that don't give no fucks. The action of running water is notably conditioned by the special relationship which holds locally between the gravity of the coarsest fragments supplied from the upstream and the force exerted by the water, a function of velocity. So the force is a function of velocity, which is a function of the pressure behind it, effectively. If this force exceeds the gravity of every fragment, the stream is able to carry away all the waste it brings. So, like, the gravity of a mountain, if the stream pressure force exceeds the force of a gravity of all these like mountainous materials, it don't give no fucks. It cuts through them, it brings them with it just like a pebble. You coming with me, mountain? Kind of like Heart Mountain. In Bighorn Basin, see episode like 370 something maybe. The outcome of its activity will be cutting of a relatively straight. Alright, let me go back a little bit. If this force exceeds the outcome, okay. Straight vertical walled canyon. If the force is less than the gravity of some fragments, the stream will fail to continue moving the coarsest of its debris, which consequently accumulates and builds up a deposit. If the force and the gravity approach are exactly in balance, the stream carries the waste in a selective manner. Progressively coarser fractions of the total alluvium are moved less in unit time, and the coarsest fraction is moved each season an indefinitely small distance. This selective action results first in the stream's failure to corrode the bottom of its channel. Second, in its going into a lateral or side-to-side oscillation. So if there's enough resistance, it starts to go around the resistance, pretty much, which is visibly manifested in the currents pursuing a serpentining or meandering course, which is what it thinks stabilized into as the pressure behind these currents was reduced, so things in front of it were not as easily cut through. So even though it was going in a straight path, pressure alleviated, then it was just a stream, a river, like a modern river. So then it started to run into resistance and take an actual meandering path. Standing water picks up rock debris along its shores and with it corrodes its margins. The outcome is to form wave-cut and wave-built terraces in the trench. No evidence suggests that this agent need be considered much of a factor. So really they've ruled out wind, they've ruled out standing water, and as we've seen already, they've ruled out glaciers, but they've applied solid reasoning for why water is eroding the trench. Flowing ice works in a somewhat different ways. Compared with running water, it erodes crudely. It does not select unresistant rock, which neither does highly pressurized currents, but that's okay. I mean, it does, but it doesn't, like, depending on the pressure. With enough pressure, it doesn't. Fails to carve to an even gradient or to reduce any area to flatness. In a valley, it produces a U-shaped cross-section and a gradient of humps and hollows. Once these agents have formed perceptible slopes, weathering and wasting work upon the slopes and tend to reduce their steepness. Thus, a vertical-sided canyon becomes, through lateral wasting, a valley of broadly V-shaped cross-section. Any steep cliff may thus become gentle through having its crest carried back by wasting while its foot remains in place. However, if aggressive corrosion carries back its foot also, it will remain steep, as are those cliffs that face a stream from the outer curve of a bend. Or like a bend. Like a bend. Bending. It's bending this way. Going around the bend, kind of like a car going around a bend and then picks up speed in the straight path. Another belief known as equilibrium theory. How far are we? Okay, we're almost. We probably can make it through this. Maybe I should kind of speed through now. Holds that the entire solid surface of the Earth is subject to a sort of streaming movement of rock debris from higher places to lower. This is unsupported except by a thoroughgoing misinterpretation of surface process. Opposed to equilibrium theory, the hypothesis of unequal activity holds that while surface process may be almost at a standstill on flat horizontal ground, it may be at least 1 million times more active in such places as the bed of a torrent, or the outer curve of a river bend. So that creates variation. These two extreme conditions are designated stagnancy and activeness. This is much more of the reality of the situation. Kind of like catastrophism. Distinctive peculiarities of the trench, a valley of the gradient of which cannot cause one river to run its whole length, and which is wide open at a low level in 6 places and therefore cannot confine a river, and yet which points to a much bigger river that flowed through and branched off while still flowing through. It flowed, branched, but had all of this current involved that just because it went the other way didn't mean that it wasn't going the same way through the trench. And yet it is an excavated valley with abundant structural evidence for its having been denuded from the surface, eroded, and with abundant physiographic evidence of its having been shaped by streams. Once again, is there any scientific answer? The making of the trench, the difficulties. We have already concluded that none of the epigene surface of the earth agents individually and within the known extent of the processes to which they give rise could have made the trench. Nothing we know of could have made the trench in the modern interpretations of things. Rivers are by far the greatest workers of erosion, yet within the received erosional theories, one cannot envisage a river that might have excavated the trench unless they envision the global flood. I mean, it's as simple as that. The reversal of streams and transference of their, and its full extent, or as best as possible to really envision its full extent by being like, oh, that's caused by the flood, and here's why, and that really gives evidence to that. These high-intensity currents are at play. Highly pressurized current flows are flowing on the surface of the Earth just like they did in shallograms. Reversal of streams and transference of their flow from one course to another is a possible but very special interpretation, but it cannot and ought not satisfy all students of trench origin. This investigator is thus caught in an impasse and has to ask, is there an unknown epigene process, like the flood? Is there a surface geological agent that in certain circumstances, like the flood, engages in activity far beyond what is generally admitted, like the flood? The making of the trench may well lie in a positive answer to one or both of these questions. The flood. The flood, like the flood. Like, there's a lot of things that have the in front, like the Great Depression. Like, are you sure that's not just to, like, make us think that was the worst to ever happen? And, oh, shit. And therefore, nothing could ever be worse. The flood. Yeah, that was the flood. There's more to be found out about this. Perhaps you, I guess this author was acquainted with Schofield, who they referenced before, who gave them a copy of this paper with the remark, there's more to be found out about this. Perhaps you... Studies showed these observations to involve only simple problems to understand which one had only to see that lateral erosion is a much more prevalent and potent process than most geologists had credited it with being. Sideways. I don't know if there's evidence of currents doing more like flowing, but then flowing with like a vortex shape in the flow. Like a cycling, I don't know, or even more like elongated vortex, or even going up like an infinity symbol kind of vortex. I don't know if there's I don't know. But much greater puzzles were in due course perceived in the great length and continuity of depth in the trench. These had long to remain as baffling enigmas. Is there a surface activity that in some circumstances goes far beyond what is usually admitted? One of the greatest unknowns, the flood, one of the great unknowns in geology is the river and its work. Many experts set about trying to tell us all about rivers. Few of them seem to want to re-examine the evidence bearing on what streams have done and are now doing. The writer has labored to show people the prevalence in scenery of lateral erosion. And then they go on to talk about there's also headward erosion, which is at the front of the current as it. So this one's probably worth just kind of looking at it like this. Lengthens a stream, so at the front of the current pretty much. A process still less perceived. In fact, nothing in all geology is less known. Any serious attempt to show headward erosion to be generally of great influence in the shaping of scenery would run the danger of being thought a flighty innovation. Although maybe that's 1964, this might actually be a little more accepted today. Let's see. It does seem to talk about it more like it's accepted. Downcutting by streams has been well estimated. Sidewise cutting has been estimated, while headward extension is no more than a qualitative assertion. Beyond question, it is a real process. The suggestion is now made that headward activity must be taken much more seriously than it has been so far. It is certainly no mere superficial curiosity. It may well be a potent process. Without headward erosion, no trench could have come into existence. Let me see. I'm going to skip this one. You can read those. I guess I might as well read it. Contribution of headward erosion. Visualize increasing rainfall. So this is all in the modern paradigm still. So they're trying to imagine how this is happening by saying, well, there maybe a lot more rainfall happened, and that's where this water came from that eroded. So it's kind of going through that. He's kind of going through that type of thing. It is unlikely that increase of rainfall will cause any novel and inceptive development in the drainage. The maximum increase in channeled surface drainage will occur in a land in which come the greatest intensification, they say of rainfall, but of the flood. In such an example, much of the new drainage will be extensions added to the old, like the growth of twigs, assuming that it's far enough down the growth pattern, like the growth of twigs versus a trunk. Like trees don't necessarily grow twigs in the trunk area. I mean, sometimes they have branches off, but they're much more likely to not have branches off, and even twigs are down the line. So like this is much more like an artery than a vein. It is a main conduit, much more so like a trunk than like a twig. So it takes a certain distance in the length of the tree to really reach the point where it branches off, and then it starts to have branches, generally speaking. Same thing goes with all types of currents, like a lightning strike, maybe like Lightning images. Oh, this idea where it's got like a main thick conduit and then it branches. The making of this kind of new channel requires headward erosion into hitherto undrained areas, and the process can go on into it. That's probably why this is not really accepted in modern science, is because they're like, dude, this is cut into mountains in a straight path, pretty much. Or like, if it's just erosion, it's cutting through mountains. Like, it's not gonna go around. Sure, like there's drainage into the area, but like to create that's a big ask. Without the flood involved, that's a big ask. I can understand. I mean, I know the flood is probably an even bigger ask, but for people to like consider. But the reality of the situation will it just will come to light when it comes to light. It happened. Like, I was an atheist once. I'm telling you, the flood happened. I used to be a staunch atheist. Like, it is what it is, dudes. I stand corrected. The observer tends to conclude that this form of stream activity needs specially favorable conditions, like the flood. One of the best... So here's an example from the Andes. Rapid headward erosion is ascribed to valleys in the slopes of volcanic islands. In Hawaii, this action has here and there resulted in convergence and conjunction of the heads of valleys, the mouths of which are well separated at the coast. The outcome demonstrates that where conditions are particularly favorable, like the flood, and nothing inhibits it, like highly pressurized currents, headward extension will appear in great strength and produce outstanding effects. It may be necessary to try to see it in a great many places where it's not only hidden, but is not even hinted at by any plain geological evidence. Do not seem to be eroding headward. Blah blah blah. Yet is not the lowering of the divide a form of headward erosion so well balanced one side against the other that in effect nothing is gained but the lowering of the surface. I'm not sure what exactly they're talking about at this point, because they're talking about like currents coming from different directions, which then like do collide and go down and up, but I'm not sure that, like, I can't envision. They don't have any images in this paper. A little surprising, honestly, but one may say every ridge that is erosionally lowered presents a case of headward erosion, negated in its horizontal manifestation by there being equal activity on opposing sides. If headward erosion is universal, at least a tendency, one must add that it shows up strongly only where circumstances provide unbalanced conditions, like highly pressurized currents that are like running into less resistance, so there's an imbalance in the pressures so that current flows through. But in no case, real or imagined, have we yet shown that the process may go on unimpeded indefinitely, yet it seems not impossible that this could happen. And this, I guess, is like, why is the trench so long kind of thought that he's getting at. And highly pressurized currents in the right circumstances could go on at what seems indefinitely for the entire Rocky Mountain Trench. Excavation of trench, was this extended headward activity a dominant factor in initiating the making of the trench? Is it strong enough to contribute an actual excavation process? So then he goes on to Though headward erosion is a more potent process than has hitherto been called into any of these discussions, not even the very considerable headward erosions that we have demonstrated within the trench are fully adequate in themselves to account for all the trench character. He goes on to try to present an alternative, I believe. This need not be a disappointment in the search for a genuine, adequate mode of trench excavation. There may be other discoverable factors, like the flood, in the trench's history, like the flood, factors which are of great potency, like the flood, and so far equally little considered. Its present-day draining is strictly recent. The trench bottom is mainly Pleistocene. The difficulty in the way of reconciling with Davis' theory is that the trench has grown among waxing mountains. What we know of it does not lend itself to the extreme theoretical simplicity of Davis's doctrine, which not sure. Let's see if we can find something on this Davisian cycle of erosion. Cycle of landscape development, a cycle of river development at the level of the drainage network, and lastly, a cycle of slope development. Okay, well, you can look into that. I haven't, so if you're interested. In effect, the trench tells us if you would read my puzzle, says the trench, Davis, Penck, and others must be left behind. It's not that simple, although it is simple. It's not that simple. We gotta account for other things that's not accounting for. That is in a purely uniformitarianism, as simple as possible in describing this one thing without really accounting for the actuality of the situation, but not actually simple because it's wrong. As Einstein said, or is said to have said, as simple as possible, but no simpler, or something of that nature. This is too simple. They made it too simple, and the reality is simple, but not that simple. Like, there's more to it. And this trench says otherwise in terms of the Davisian cycle. Today's trench characteristics are staged in an evolution more complex than anything those two older masters of geomorphology recognized. There is simply no reason for supposing that the trench could have survived in finished condition from the Eocene, or that it would have required the time from Eocene until now for its making. Though the Grand Canyon of the Colorado may have been excavated in no more than post-Pliocene times, some shallower valleys may have needed much longer. The trench's true beginnings may be ancient. Which I don't know what the word ancient means to him. In the region now occupied by mountains southwest of the trench, some of the orogenic structure is supposed to have existed from time before the end of the Cretaceous. In the Rocky Mountains, on the other hand, the strong tectonic features were initiated at the opening of the Eocene, although definitely the Rocky Mountains date to end of the Cretaceous as well in part, so I'm not sure. Again, this is 1964, so these details might be a little, like, not quite up to date. Let's see if I just Google when did the Rocky Mountains, yeah, like, I mean, that's just Google. I know there's evidence of other, like, it's more extensive than the Eocene, which Eocene is like 55, yeah. Definitely dates further back than that. Trench now occupies a small part of the structurally low country between the Central Rockies and these other mountain systems. And it is surmisable that that belt was, in its earliest stages, a relatively low surface between the flanking uplands, which, so this is his theory, I'm not going to go into it too much, but I think there's probably some merit to it in terms of how the flood shaped the region, although there's definitely colliding terrains and all sorts of stuff, so maybe it's a little too simplistic again. But I like where he's kind of like building it from some starting point of just like a lower terrain between higher terrains, and over time it takes the shape that it is today. But so then he just keeps going on with it there. Some may suspect that the agency of the Pleistocene ice has been insufficiently considered. It is evident that some Pleistocene ice did actually occupy the bottom of the trench. The evidence of glacial work thins out on the valley walls. In fact, pre-Pleistocene stream terraces and alluvium survive there. Nor has the trench a U-shaped cross-section such as an erosive glacier is supposed to give the valley. Furthermore, some of the terraces are of decayed rock, a piece of counter-evidence with respect to icework. And some tributary valleys have contained placer gold deposits and quite evidently never held erosive glaciers. None of the outlets of the trench show any sign of having been greatly enlarged, as they might well have been had moving ice poured through them. It can be concluded only that Pleistocene ice in the trench was thin and sluggish. Though it left its mark in places, it contributed very little to the digging of the valley. In general, the evidence is reminiscent of certain other parts of British Columbia where Cordilleran ice sheet did not consist of actual moving ice. A completely detailed history of the excavation of the trench cannot yet be offered, but the way is open. In a problem of this sort, there are greater tiers of evidence never yet looked at by a geologist. All this could advantageously be studied in detail before the answer can be deemed to approach finality. This evidence includes such remote classes of facts as the present-day distributions of living species of plants and animals. I thought this was kind of interesting. I don't know what to really say about it particularly, but I'll hit that again. Not all of them have a clear indication, but one that does is the range of Cordilleran waters of the landlocked salmon, or kokanee, a fish whose fate may well be the immediate outcome of some quirk of drainage history, and that in turn the result of a diastrophic movement. Then there is the remarkable mutually exclusive distribution of the two western Canadian lilies, which are debarred at present from mingling with each other at the Purcell Selkirk watershed. But what about their past? At present, one can say that trench making is no extremely rare result or unique combination of geological events and conditions. Small trenches ought not be uncommon. Great ones may be few, but need not be insoluble enigmas. That's the end of the paper. We did it. And it's worth going back again to, I believe it was maybe here. Very early. Oh, maybe here. Wherever they said trenches in all parts of the world, there are valleys that, though smaller, have nonetheless the same kinds of earmarks. Global flood. Another paper, just to read my writing here, another paper which appears to show that modern interpretation, like many conclusions in science, which are based on incomplete reasoning, takes the faulting cause of the Rocky Mountain Trench as fact and no longer rigorously considers whether or not it is the case. We don't really consider it anymore. structure and dynamics of the Southern Rocky Mountain Trench. They even say the level of seismicity, but specifically the style of faulting on the Rocky Mountain Trench remains poorly known. So even though we've concluded that it is caused by faulting and not surface processes, but like deep down earth processes that are propagating to the surface, but not erosion at the surface. Even though we've concluded that, it's still not really like well known. It's poorly known. We don't really know what's going on. Certainly we're looking in some ways, but we've already accepted that it's a fault, so we don't, like, whatever we see, we're seeing the fault from some angle, and like the data doesn't quite match up, but it matches up enough that we like conclude, yes, this is evidence for our interpretation. Which happens with ammonites. Oh yeah, there's so much evidence that ammonites are fossils and are not caused by current flows because every paper starts with that assumption since like 1800. So yeah, of course there's lots of evidence if we're analyzing them from that angle. Yeah, they look like fossils. So yeah, but that doesn't mean they are. There's really not papers that are considering it rigorously whether or not they're fossils. There's really not papers still looking at this and saying, is this caused by a fault? I don't think. I might be mistaken. I haven't that thoroughly looked, but I couldn't even find more recent papers. Anything more recent was like said the word fault in relationship to it. Alright guys, this is long enough. It's 2:08 here a.m. I gotta go. Peace out. Thanks for hanging out. I hope that was worth your time and all, and enjoyable. I know it's kind of technical, just reading a paper. Might as well dim the lights, lay down, close your eyes. It's a little too late for that suggestion, but just listen. Okay, peace out. See you guys next time. Later.